So this is actually the physical vapor deposition unit, and this is the source, this is the shutter, this is the substrate. So when you remove the shutter, it will be deposited on the substrate. But you have to have an idea that how much is the thickness, okay? Or because that is, I mean, always actually thickness, like let's say that you want some particular property, so that particular thickness is very much important. So this thickness actually is being measured by this called DTM crystal or FTM crystal. Okay. So this is actually, it looks like this one you can see, and this is that port, and where one single crystal silicon is actually this is looks like. Next slide I'll explain, I'll show you some more picture, so there you will be knowing. So this one actually being placed here. Okay, so this is the DTM crystal, how it looks like, and this DTM crystal actually will tell you this how much is the thickness. This is that how the DTM crystal is looks like, and this DTM crystal has both side, top electrode and bottom electrode, and this is how this crystal, individual crystal is looks like. An individual, I mean one crystal actually, this is that assembly that where it need to be fixed inside the chamber. So you have, from this packet you have to remove one piece, and that is actually you need to fix it here itself. So in this DTM crystal assemble, so this one that is actually sensor head. So this is the sensor head, 2 is the crystal monitoring cable, 3 is the flame, uh, 4 is the cooling tube. So here also the DTM crystal will continuously oscillate when you run this, I mean start the machine instrument. And that's why actually due to this high frequency vibration, that there is actually heating will be there. So you should have some cooling facility. And finally you should have one thermocouple. That thermocouple actually can measure that temperature if there is some overheating or other thing. Okay, so this how the lithium crystal is looks like. Now this film thickness monitoring, FTM, or it's called digital thickness monitoring called DTM. So these quartz crystal are used to determine that thickness of the material deposited. So today's class actually will be knowing that how it works. The quartz crystal is placed in a vacuum work chamber, and one face of this crystal is exposed towards the deposition source. So this one, this surface, so this is one surface, this is other surface. So this surface will be exposed to this deposition surface. So this surface will be in this side, and this arrangement will be placed here. So when it will be deposited, it will be deposited on this side. Okay, on this side. And this such that the material is deposited, that it will coat the crystal. So what is happening, I want to make a deposition here itself parallelly, that it will deposit on this DTM crystal also. And in DTM crystal, that is in a oscillation. Okay, so during oscillation that there will be a deposition. Okay, and when during oscillation, when there will be a deposition, there is a continuous, it will be have, it will mass will increase, so its actually oscillation frequency will decrease, and from that actually decrease of this oscillation frequency we are going to measure the thickness. So the system that function as a oscillator whose output is controlled by the frequency of this crystal oscillation. So if you start the machine, so this single crystal silicon will start oscillating, and as material deposited on the crystal, so frequency is modified. Okay, so frequency is basically decrease. So how, I'll show you actually how it's decreasing. And if coating without that FTM, a cover is required over the crystal to keep it clean. So DTM crystal actually, I mean, like actually if you not use the DTM crystal, sometimes what happen, in a chamber there is a 2 DTM crystal. Okay, so 2 DTM crystal arrangement is there. So suppose that you are using one, so other one better actually need to be covered, so that unwanted deposition will not be there. And time to time, this after deposition you need to clean it. So a straight edge, that scalpable blade may be used to, I mean very gently, that scaf of previously deposited coating from the chamber part of the crystal. So this part is very important. Like after few deposition, 2 3 deposition or 4 deposition, You have to clean the DTM crystal. And if you not clean it, sometimes actually it will give some errorful result. So some coating can be removed using a cloth with little alcohol or with some, very fine this polish. And only a center area need to be clean. So center area means actually it will be placed here. So this, this portion actually will be exposed. So that portion need to be cleaned. And a thickness monitor measures how much material deposited on its sensor, and most deposition processes are at least somewhat directional, and the sensor and the sample generally cannot be in the same direction from the deposition source, because otherwise shadowing effect will come. So that means this is substrate. So here I should not put it. So I should put it in this, maintaining some angle. Otherwise, what will happen? That some shadowing effect will come. Okay. So this is actually this positioning very important, and uh, that should not actually like make an obstacle to this normal path to the substrate. And therefore, the rate at which the material is deposited on the sensor may not equal to the rate at which is deposited on the sample. This is very important statement. So already we have seen that here the straightforward is depositing, but here this is actually maintaining some angle. So now how do I adjust the thickness, whatever thickness is depositing here by this crystal, which is kept sometimes inclined? So that is actually I'll explain. So the ratio of the two rate is sometimes called that tooling factor. So what is the ratio of these two? Like actually the deposited on the sensor and that deposited on that sample. So this ratio, okay. So is called tooling factor. For careful work, tooling factor should be checked by measuring the amount of material deposited on some sample after the fact and comparing it what the film thickness monitoring measure. So that is, so tooling factor is very important. In fact, the tooling factor regular basis you need to monitor. And if you not monitor the tooling factor, what will happen? That again DTM will show some deposition, means let's say that it will show 100 nanometer, but your actual deposition is 60 nanometer. So this kind of problem will come. And many technique that might be used depending on this thickness characterization of the film, like surface profilometry, ellipsometry, dual polarization, interferometry, scanning electron microscopy of this cross-sectional sample. So this question I'll ask definitely in your exam, maybe in your quiz, like next week, that actually what are the technique can be used to measure the thickness of the film. So that is actually surface profilometry. Later on, I'll explain how it works. So this surface profilometry, like there is a stylus movement, and this stylus actually will move, and you need to make a scratch. Let's say you have a film and you need to make a scratch, and then actually this stylus move, using the stylus movement, you can you can measure the depth of the scratch, and that is depth of the scratch is nothing but the thickness of the film. Let's say that you deposited some material on glass substrate. Okay, so let's say if you have a stainless steel tweezer, so your needle, so using the needle you can make a scratch on glass. So can you make a scratch on stainless steel tweezer on glass? Scratch is possible? Can anyone? Is possible? Anyone, please? Is it possible to make a scratch? Anyone?
No, sir, I don't think so.
Why?
Because glass is harder, no? If I'm not wrong.
Correct, correct. So that is the reason. So that's why that if you deposit on glass substrate, easily that you can use like stainless steel needle, or maybe it's the tweezer, that is actually to make a scratch, because in the laboratory that is generally easy practice. So you can make a scratch, and then actually you can just measure that profilometry. And second is the ellipsometry, that is actually by optical method you can measure. Then dual polarization interferometry, there is also optical method is using for measuring that this one, but in this ellipsometry and the dual polarization interferometry, you should have some idea about this refractive index of your deposited material. Or if you don't know, so you can put it some with arbitrary value and have to optimize. Scanning electron microscopy with cross-sectional samples, that is actually very much effective technique, and it can give you the accurate value with the picture. So if you make a cross-sectional cutting and then go for scanning electron microscopy, you will get the thickness. So now this how the tooling factor is being calculated. So Fm, okay, is what is this one? So correct tooling factor is Fi, that is initial tooling factor, multiply the Tm by Ti. So Tm actually is a measured thickness, okay, and Ti is the thickness indicated by the instrument like FTM. So what you will do, first time when you measure Fi, you put it 1 and you just do the deposition, then means this Ti actually will be, let's say, 100 nanometer. It shows by your Dtm crystal. Then you measure Tm by any of this technique. Then actual value you may get 30 nanometer only. Okay. Though this 30 nanometer, you put it here. And then you get that Tm. This Tm actually next time you have to put it here. Okay. So initially actually whatever the value is there, so that is actually, I mean, just to start the optimization. And then once you get that FM value, this FM further you can optimize and you can check it actually you are reaching to how accurate. So that's why the tooling factor is very important, particular in thickness monitoring. So this tooling factor part is clear, or anyone has a doubt? Please do ask. I'll move to some other topic. This is clear, the tooling factor. And why the tooling factor is important, like first time deposition, you have to optimize at least 2-3 times, then only it leads to that. Suppose that you are cleaning the chamber, your hand actually touched here. So this is actually made of some kind of metal, thin metal rod. So it may little bit displaced. If it little bit display, what will happen? The distance will change and tooling factor will change. Then it will be a problem. So that's why the time to time, the tooling factor need to be cross-checked. Okay? Because if you not cross-check the tooling factor several times in thin film deposition, these are common mistake. So whatever the deposition we are doing, but we will not get the exact deposition. Because of this from improper, I mean, optimization of this tooling factor, or sometimes not tooling factor, if you not do for a longer time, that it will end with a mistake. So these are actually very important practice need to be done. So time to time this cleaning is very important for this DTM crystal. And second part is that tooling factor adjustment or tooling factor optimization. Okay. And how to measure the thickness of the film? These are actually available technique for thickness measurement. Now actually I just like to show you this how it works. So with one very nice this video. So this, yeah, so this thickness monitoring. So yeah, so how it's happening, that homogeneous elastic plate set into the mechanical vibration have resonant frequency that depends on this dimension, elastic moduli, and importantly the density. So these are the important parameter that will actually finally it will decide this mechanical vibration of this crystal. And additional mass in the form of the deposited film alter the resonant frequency by effectively changing the properties of this composite vibrating plate. So what will happen, that if something deposited on the DTM crystal, immediately mass will change. So that part actually we will see how actually it's it's giving the result. Yeah. So that thickness is the principle that underline the use of this crystal oscillate to measure this film thickness. And this DTM crystal, so this it's called 80 cart quartz crystal, that is actually cart 35 degree with respect to axis of this Z, axis. Okay, and this DTM crystal actually top and bottom two electrode will be there. And then actually you can previous picture also I have shown that one side actually yellow colored and other side some circuit is there. So this kind of arrangement, so both electrode, the metal film deposits, some metal film electrodes are deposited on both side face of this crystal. So basically, but we are going to use in this assemble, but previous case actually I have shown only one side actually can be used, but in some other arrangement both side can be used. But in whatever the previous picture I have shown, they are one side. So then it is then mounted in the deposition chamber close to the substrate. So this is actually the deposition chamber, and this is this DTM crystal here. So this one actually don't be confused. So this is one particular arrangement, but whatever the previous slide I have shown, bottom and top electrode will be there, but there is a different arrangement. So now actually let's have a look at how it works. Yeah. So this fundamental, that frequency f of this shear mode is given by f equal to vq by twice vdq. So vq is the velocity of this elastic transverse wave normal to that crystal plate, and this dq is the thickness of this crystal. So this is actually normal frequency without any deposition, how it actually this oscillate of this particular crystal. Okay, because this is a piezoelectric material, so of course it will oscillate. Then what happened, that if dm, the deposit on this on one of the crystal electrode, then thickness increases by an amount is given by d equal to m by a rho f. So this is actually what is a rho f, like this is nothing but, let's say that d is the thickness, a is the whatever that cross section is deposit, and rho is that if you know the density. So this is actually d into a multiply, that is actually volume, and volume into density will be mass. So that is that formula d. So this that is the this coming. And now that f equal to, as I already observed, that vdq by twice vdq. And then here this with this additional mass, that whatever is actually is coming. So this is actually contribution from this additional mass, so it's coming m by a rho f. So this is frequency contribution from this additional mass. So now if you do that, actually the differentiation, so what is happening, df vdq a, then rho f by 1 minus m square dm. And just actually if we just simply do it actually. Okay, so this is just nothing but that vdq a rho f. So vdq a rho f, that is actually nothing but the f by m. We can write in this way, f by m film thickness, this one, and by m. and then this one actually just f by f we first we are writing, and then it is coming that f square by m dm, and by the twice m. If you put this value of this f from this previous one, so it's coming like this, because in the previous slide we got the value of f like this, and maybe this particular video I'll send to you. So final actually derivation, let's have a look. So this is coming like this. So this is f square. So what is a? I am taking it out. So this one f square. So twice by a, and rho. This is actually one this kind of this sorry, this vq by 2, that is actually is defined as a frequency constant whose value is 1656, that kilohertz for 80 quartz. And this, there is a negative sign is coming, so that is actually that it says that equation signifies a decrease in the frequency as this added mass increases. So if added mass increases, so there is a decrease in the frequency, and df is proportional to f square. So what is indicate that at a higher sensitivity is obtained for a high frequency. So I mean up to 100 kilohertz is actually that frequency range can be oscillated by this crystal. So that means little bit high frequency is required to get that accurate value. And this is, you can see, with the deposition or with the impact of the deposition, there is a decrease in that oscillation or is normal frequency. So in previous slide already, I mean page, we have seen that what is the normal frequency of the crystal. Then if there is a deposition, with deposition, how this df is changing. Now we have to measure. We should have actually two basically crystal arrangement. One crystal will be placed inside the chamber, another crystal will be outside the chamber, and we can monitor other crystal actually without deposition, and this is with the deposition. Then only that we can monitor that how much is that deposition. Yeah. So this is actually that actual chamber, and this is the, as I told, there are actually, this is that your actual DTM crystal, and another DTM crystal will be there outside the chamber, and with this actually relative deposition. So one, it will be deposited here, and there actually continuously some mass will be deposited, and hence its oscillation frequency will decrease. And from this decrease of this oscillation frequency, in comparison with that without deposition, this one also will oscillate, but there will be no deposition. So you will have to will get the exact picture that what is the deposition is happening. Now question is that here whatever the deposition, and in this substrate deposition will be different, but that is actually we need to adjust from this tooling factor. So tooling factor will help you to make some correction. Okay. So like actually, I mean using the tooling factor, you need to, I mean although it's not depositing here, but you have to, you will get the exact picture what is happening on top of that substrate. So yeah, so this is, I guess, yeah. So here actually like an oscillatory quartz crystal with a natural frequency 6 megahertz is positioned inside the chamber above the source by a side of the substrate in such a way that the vapor is deposited both side of the substrate, and on, I mean define the area of, this is actually for a special case, we should not go. So whatever that we understand, so up to this is sufficient. So basically that idea is like that there will be a 2 DTM crystal. So one DTM crystal actually will be placed inside the chamber where it will be deposited, and with the deposition there will be a mass increase on the crystal. And then what will happen that with the mass increase, that its normal frequency oscillation frequency will change, and we have another one DTM crystal outside the chamber, and that is also will oscillate. And then with that comparison of this frequency change, will measure that thickness. Now question is that thickness whatever will be the deposition pattern here and will deposition pattern here will be totally different, and that's why tooling factor is very important and that need to be used. So since here we are talking about the deposition, so time to time cleaning is very important. If you clean it systematically, then only you will get that exact information of this thickness. And another one thing, there are actually two different monitoring units there. One, it will give you the thickness, another will be the rate of the deposition. So rate of the deposition, how it will coming, like let's say that number of atoms, so number of impingement. So that is also easily can be measured, like number of impingement is proportional to this increase of this mass. So from this increase of the mass, so rate of increase of the mass, that we can get a that precise measurement of this rate of deposition. So up to this is any question you can ask. Any question so far can be asked. Otherwise, I'm going to wrap up now. Any questions? So I'll take the attendance. Okay. So is there no more questions? So then just I actually would like to ask one question. So let's say that you are doing the deposition and in that deposition chamber, suddenly actually, if you observe that your rate is very high, so what you will do? Suppose your depot is your, let's say that you are doing the deposition, it's actually let's say 1 nanometer per second. Suddenly you observe it reach to 10 nanometer or 20 nanometer per second. What you will do? Can anyone? Can anyone tell?
So increasing the temperature would control deposition.
Increasing the temperature controls the deposition. So increase the
Yes,
temperature of
sir.
what?
Inside the I mean that metal which we are used for.
So that means that you are talking about basically the voltage regulation, right? Because this is a resistive
Yes,
heating,
sir.
so
Yes.
voltage regulation you have to you can,
Yes,
that
sir.
is one way. So this is actually common problem. So sometimes you may observe that you are doing the deposition, suddenly it shoot like 1 nanometer to 100 nanometer is reached. So first job is that actually if you want to protect your sample, because in that case actually what happens is suddenly it will be huge deposition. First job is that you close your shutter, because you don't want your sample should be damaged, right? So close the shutter. If that is happening, close the shutter and then adjust that your deposition by using this what is called that your voltage meter. But in voltage meter also, if you are unable to do it, suppose you reduce the voltage, still you saw that this very high rate of deposition is there. So then the reason of this kind of problem is the failure of the Dtm crystal. So Dtm crystal has a life. So with time actually it may gone. So then what will happen that that time actually you means from source side what you can do, reduce this voltage. That is actually so that what happened that heating overheating will be less. Substrate side you can close the shutter. So if you close the shutter, at least your unwanted deposition will be not be there, and you know before shutter close how much is the deposition thickness. Then you wait until your rate is optimized, then again you will open the shutter. So the shutter side, and that in this case also if you are unable to do it, like shutter need to be closed first, voltage meter need to be reduced immediately, still you not able to observe, then that means there's something wrong with the DTM side. So then actually you have to change the DTM crystal. Okay, DTM failure. And why DTM failure is happening? Like I told, during the oscillation, if temperature is high, so it may break sometimes, the DTM. And if DTM breaks, immediately some arbitrary value it will show. So these are practical things actually is happen. But first thing is that you have to close the shutter. Second, reduce the voltage meter. So reduce the voltage so that overheating part also should be nullified. And third, that you have to pay attention from that in the DTM side, DTM crystal side. Okay. Yeah. These are the practical thing. Okay. Thank you. So wish all of you a very happy Ganesh Chaturthi tomorrow. So again, that we'll have a class on Monday. Thank you.
Thank you, sir.
Thank you, sir.